If you're watching on the live stream, I'm not sure what's going on in Marcus. So I'm texting our grad student and hopefully we'll be going in a minute.
Professor, can you hear me?
Yeah, can you hear me okay?
Yep.
Awesome. Okay, so let's get started. A couple quick announcements. So this week we are finishing up our last section of chapter 1 today, and our chapter 1 quiz will take place on Friday. So you will need to find a 1-hour period on Friday to submit your chapter 1 quiz. It will open just after midnight on Friday and then close at 11:59 p.m. So you can really take it anytime on Friday, but you need to make sure you start by 10:59 p.m. to ensure you have the full hour. It's 10 questions, multiple choice, similar to what you've been doing on the mini quizzes. So the best way to prepare is to go back and look through your mini quizzes. You can see what you got wrong now that the due dates have passed. And for the 1.10 quiz on Wednesday, you'll be able to see Thursday morning anything that you may have gotten wrong. So definitely feel free to stop by, drop in help this week if you have any outstanding questions from the mini quizzes. Also, I want to mention that the reviews coming up this week, there'll be a review on Thursday and Monday, like there have been the past couple weeks. This week it's going to be on sine and cosine, which we're going to introduce a little bit today. So if it's been a while since you've worked with sine or cosine, then that review might be for you. And so again, if you can't attend, those will be posted under getting started once the Monday review has happened. So as I mentioned today, we're going to cover our last topic in chapter 1, which is periodic functions. So I'm going to go ahead and switch over to the dot cam. All right, get that lined up. All right. So what is a periodic function? Okay, so a periodic function is going to be a function that repeats its values on regular intervals. And so those intervals where a function is repeating is called a period. Okay, so I'm going to show you some examples of periodic functions so you can kind of get a visual representation of what this means, this repetition. Okay, so the first one here, we see that this function goes up to a peak, comes down, kind of does a little dip, goes up to a peak, comes down, does a little dip, and we can see that the pattern is repeating. So if I asked you to draw what would happen next, you would be able to predict what the next part of the pattern looks like because we can see that it's repeating over time, right? And you kind of see the solid part to show what one period would look like. And then it starts again, right? So on and so forth. This is another example of a periodic function where you can see we have sort of the tall wave and then the short wave and then the tall wave and then the short wave and the tall wave. And then we would predict that next there would be a short wave. So we can see that that is repeating. The first two are a little more obvious that they're periodic, although not completely. But then sometimes we have data that is a little noisy, right, is what we call it. So it's a little chaotic and it's a little bit harder to tell that there is a pattern. And so sometimes you have to look at it for a little while to really see what's going on. And so if we look at this function here, and we look at where it starts, we can kind of see this like bottom piece repeating, right? And so if we kind of look at what happens, we can kind of see that the same thing is happening again and again. See the twin peaks up here, the twin peaks up here, up here. So we can kind of see that they are repeating in some sort of way, but for this one, at least for me, it's not as obvious. So sometimes you really have to look at something for a little while to notice if there's a pattern. But If you do notice it, the value of the pattern is that we could then use it to predict what will happen later, right? And so that's one of the reasons why calculus is so powerful in a lot of ways, is that eventually, once we get good at it, we can use it to predict what will happen at a later time. Okay, so these are just some visual examples of what periodic functions look like. But let's talk about, mathematically, what do we want to know about them? What do we want to do with them? What sorts of details are going to be important to us? Okay, so there's two sort of main things that we're going to be interested in determining on any periodic function. So the first part is the amplitude. So the amplitude is going to tell us how far we vary from the midline to reach the extrema. So what does that mean? That means if you were to figure out where the middle of the function is in terms of up and down and draw a line, I want to know how much do you go in either direction, either up or down. So it'll be the same amount up or down because it's the midline. So it's how much you vary from that middle part to either the maximum or the minimum, right? And that should be the same number since you're at the midline. So we do have a way to calculate this. So when we look at a function, we are going to find the maximum y value, right? So how high does it go up? Minus the minimum y value. And then we're going to divide by 2. So if we look at the maximum minus the minimum, that tells us the span, right, of our function. And if we divide by 2, that's half the span. So that tells us how far we would vary from the midline. So again, we're looking for the maximum y value minus the minimum y value, and then we divide by 2. That's going to tell us the amplitude. Okay. The other piece that we look for is called the period. So notice the amplitude was sort of the up and down. The period is going to be the left and the right. So the period is the amount of time, or the distance, in terms of the independent variable it takes the function to complete one cycle. So how long does it start? How long does it go until the pattern starts to repeat, right? Is sort of the question. Does it start to repeat every 10 units, every 2 units, every 12 units? So we're looking at the horizontal numbers and the pattern to see how long it takes to repeat, okay? So let's take these two ideas, this idea of amplitude with our formula and this idea of period, which is repetition, and see if we can look at this particular graph or this periodic function and determine the amplitude and the period. So you can see how I've labeled 1, 2, 3, 4, 5 up the axes. This is also counting by ones. I've just ticked off the tick marks. Okay, so I want you to take, I don't know, a minute and a half. See if you can put this into play. I'm going to move that down a little so you can see the formula. See if you can calculate the amplitude and the period for this function, and then we'll go through it together. Okay, so take about 30 more seconds. All right, So let's go through this. It's our first one. So again, since we've never done this before, it's totally fine if you were sort of not entirely sure what to do. So we'll go through this one pretty thoroughly so you have a good idea of how we're applying this. So for the amplitude, we want to start by finding the maximum Y value. So we're looking at these peaks to figure out how high they go. And so what we see is that the maximum Y value here is going to be 3, okay, because it goes up as high as 3. So here we have 3, which is our Y max, minus, and now for our min, we want to come down to where we sort of bottom out. We kind of see, okay, looking across, right? So that goes down to about -1. So be really, really careful with negative numbers because we're subtracting. And then we have to divide by 2. Okay, so 3 minus -1, right? The negative and the minus are going to cancel. We have 4 over 2, which is 2. So our amplitude is 2. So what does that mean? That means if we were to draw in the midline, which is the line right in the middle of our maximum and minimum, we'll draw that in like here. Our midline. Since the amplitude is 2, that means we vary up by 2 to get to the maximum Y value, or down by 2 to get to the minimum value. Okay, so if you go 2 units in either direction from the midline, you're going to reach the extrema. That's what the amplitude is telling us. Okay, now for the period, we're looking at how often this repeats. So you can pick any part of this graph to figure out like when does it start to repeat. I sort of darkened one part of it prior to the start, so that's what I'm going to use. But if you picked a different point, that's fine. You should still get the same period. So how do we figure it out? We want to see where we start and then where we start to repeat. So I picked this as a starting point, which you can see is at the tick mark -3. And then I look at the whole picture until I get to the point where I start to repeat. So I start to repeat at this tick mark, which is at 2. So to go from -3 to +2, that is 5 units. So that means that the period of my function is going to be 5. So how long does it take until my function starts to repeat? So notice that when I get to this point, I start this up part again, right? Or I could have started here, the up part, right? So I'm looking for repetition, and then I'm looking at how long it took to start to repeat, okay? So that's how we're going to find amplitude and period. So we're going to practice this on the other 2 periodic functions we saw before. And hopefully now that we've gone through that, if there are any sort of outstanding questions, it makes sense now. So here are the other 2 functions. So what we're going to try to do is we're going to try to approximate the amplitude and the period for these 2 particular functions. So these are the same ones we looked at right at the beginning. It's not perfect, so just try your best to approximate. So you can kind of see that this is not at a nice whole number like we had before. That's fine. We're trying to approximate to the best of our abilities. And then for this one here, like I said, this one's a little bit noisy, so you're going to have to do some approximating. It may not be perfect, but give it your best shot, and try to find the amplitude and the period for both of these functions. I'm going to give you about 2-3 minutes, and then we will go through it together. Okay, take about 30 more seconds. All right, so let's go through these and make sure that we're feeling okay identifying some numbers here. So we'll start with the first graph and look at amplitude and period. So for the amplitude, what I am noticing here is that on the axis, I'm counting by twos, right? So if I'm looking for, the maximum value here in sort of my visualization, I divided that in half, so that would be 3. So I said, okay, that looks like it goes up to about 2.5. Okay, so for me, my Y max value was 2.5. As long as you're somewhere in that range, then that's a pretty good approximation, right? Somewhere between 2 and 3. If you have like 5 or 6, then you're a little bit off, right? So we want to approximate how high we are. So I have 2.5. So Y max minus, now I need to figure out Y min. So since I'm counting by twos, this is -2, -4. I'm trying to figure out the value of this minimum value. So again, I'm going to approximate that as -0.5 or -0.5, but it should be somewhere between sort of 0 and -1 that we're approximating. And then divided by 2. So 2.5 minus -0.5. Again, if you subtract a negative, the negatives cancel. So this is 3/2 or 1.5. So the amplitude here is 1.5. And again, that means if I were to draw in the midline, that I vary by 1.5 in either direction to reach the extrema. Now, in order to approximate the period, I need to pick a point on my graph and see how long it takes to get back to that original point to start repeating. And again, you can pick any point to start at, but you should get the same period no matter where you look, because the period's the same no matter how you sort of move things around. So I'm going to pick the point that's just at the origin, right? So I'm at the peak of this hill. So I want to keep going till I get back to the peak of the hill. Okay, so here I see that in order to go from this peak to repeat, it takes me 6 units, right? I went from 0 to 6. So that gives me a period of 6. And again, you may not have picked that same point, but if we picked like, I don't know, top of the little hill, right? And we kept going until top of the little hill, right? We can see it's roughly -3 to +3, which is again 6. So as long as you're mapping something to the point where it starts repeating, you should be getting 6 as the period. Okay, so let's look at the second one. So again, this one's a little more noisy. It just means it's a little more chaotic to try to sort of figure out, but hopefully we can get some good approximations here. So I want to point out that the scale on the up and down is -5 to 5. And then across we have 11, 12, 13, 14 labeled in case you can't see that. So for the amplitude, again, we are trying to figure out the highest point and the lowest point. So if I'm looking at the highest point here, this one here, if this is 0, I'm going to call that 4, right? If this is 5 and this is 0, that looks to me to be approximately 4, as long as you're somewhere in that range. That's fine, right? And then the lowest point, right, is down here when we get to the very bottom. So I come over here. And again, to me, that looks like -4, right? As long as you're roughly near -4, so, you know, -3.5, something like that, that's totally fine. So we have 4 minus -4 divided by 2. Again, we're being careful with our negatives. We have 8 over 2, which gives me an amplitude of 4. So you can see that the midline is sort of dotted in here. So the amplitude tells me that in order to get to the maximum or minimum, which are the extrema, I would have to go 4 units from the midline. Okay, now for the period, I want to see how long it takes me to repeat. So if I start right at the beginning of where the picture is, and I keep going until I get back to the point where I'm down here again, I can see that that is where I then start to repeat. Okay, so I need to figure out how far I've gone. So I'm counting by ones here. So this is a 10, 11, 12, 13, 14. So this is about halfway between 11 and 12. So I go from 10 to 11.5, right? So I've gone 1 unit plus half a unit. So I'm going to say that the period is 1.5. So every 1.5, this is in years. I don't know if you can see this, but every 1.5 years, this pattern repeats. Okay. And so this particular function is measuring something that has to do with the synergy of certain planets, which is why it's sort of chaotic. But every 1.5 years, the pattern starts to repeat. So we can predict what these patterns are going to be in the future. So these are sort of generic examples of periodic functions where we look at things with data and things that are a little more, I won't say messy, but a little more not as smooth as what we typically look at. So one of the things we're going to do in this class is we look at a lot of things that happen in biology and nature. And it turns out that a lot of the functions that we find in the wild, if you will, in nature, are going to be modeled by sine and cosine functions. And so we're going to go ahead and say that most of the time we're going to consider what's happening within the sine and cosine functions to help us understand periodic behavior. So we're going to do a little bit of a review of sine and cosine in terms of periodic functions, just so that we see how the things we've been talking about applies to sine and cosine. If it's been a while since you've done sine and cosine, like I said, there's going to be a review of that on Thursday and Monday. But otherwise, you know, we'll mostly just be incorporating it in things that we do. One thing I do want to mention, although we don't do a whole lot of calculation with sine and cosine in this section, if you are plugging a sine or cosine into your calculator, you need to make sure it's in radians. So everything we do here is going to be in radians because we're looking at the graphs. We're not really looking at degrees or triangles or anything like that. So make sure that your calculator is in radians if you're doing anything with sine or cosine. Okay. So we're going to start by talking about the sine function. So one of the characteristics of the sine function, when it's just sine, so no numbers attached to it in any way, is that it starts at 0, 0. And this is going to be important because later we're going to be looking at all sorts of different things and saying, well, is this a sine function or a cosine function? And so we need to think about what are the different characteristics of these two functions to help us distinguish. So if sine is all by itself, right, with no like number in front of it or next to it, which we'll get to later, it goes through 0, 0. And I want to point out that after that, sine starts off increasing, right? So we're increasing to the maximum. So when we talk about sine and cosine, but sine here, in terms of what we've been looking at, which is amplitude and period, we can use what we know from pre-calculus to be able to figure out these things like amplitude. So the maximum value that sine takes on is going to be 1. So our y max is 1. And the minimum value is -1. So sine varies between 1 and -1 forever and ever. right? Which means that our amplitude we can find because we do the maximum value minus the minimum value divided by 2. So we get 2 over 2, which is 1. So the amplitude of sine is going to be 1, right? So 1, 1, which means we vary from the midline by 1 unit to get to either the maximum or the minimum, okay? Now for the period of sine, right, we're interested in when it starts repeating. So if we were to start, at 0, we get to 0 again here, but the pattern doesn't repeat here, right? It doesn't start going back up again. So we have to keep going. But when we get to the second 0, we see that the pattern starts again, okay? And so the period goes from 0 to what is 2 pi, right? So just about 6.2. So the period of a sine function is 2 pi. So when you're looking at pictures in terms of periodic functions and you see something crosses a little bit after 6, that is very likely 2 pi. And if you cross a little after 3, that is likely right at pi, right? These are common values. So I did it from the 0 to the 0. If you had done the same thing from sort of the peak to the peak, because again, the period is going to be the same no matter where you measure it, you will also see that it's a little bit more than 6. And so the period is 2 pi, okay? So this is what the common sine function looks like. The amplitude is 1 and the period is 2 pi, okay? Now let's also look at the cosine function to see what the differences are, okay? So cosine of x, just like sine of x, is a periodic function that comes up quite a bit in nature. For cosine of x, the maximum and minimum values are the same. So cosine also varies between 1 and -1. So our maximum and minimum values are the same, 1 and -1, which means that our amplitude is going to be the same. So we get 2 divided by 2, which equals 1. So our amplitude is 1. And unsurprisingly, the period is going to be the same, right? So if we were to start at 0 and we keep going till we get to the same place to repeat, it happens a little bit after 6. And so the period is 2 pi. So what are some of the differences with cosine? So notice that cosine starts at a maximum. Okay, so sine started at 0, cosine starts at a maximum and is decreasing. One of the things that becomes tricky is as we start to change the sine and cosine by adding things to it, then the things that we would normally look at, like starting at 0, 0, right? If we shift it, that's no longer going to happen. For cosine, if you start at a maximum or a minimum of the function, it is likely to be cosine. So if you start at a maximum, you have cosine. If you start at a minimum, you have negative cosine because it got flipped, okay? And we'll talk about this as we do some of the problems going forward. But the amplitude and the period are the same for both functions. And it turns out that these functions are related in that they are exactly the same function shifted by pi over 2. Okay, so if you were to take this function and you were to shift it over pi over 2 units, then this part right here would shift to the origin and you would have sine, right? So it's unsurprising then that the amplitude and period would be the same because they repeat in the same intervals and they have the same maximum and minimum values, okay? So that's our very, very brief overview of sine and cosine. And now what we want to do is we want to take that and start thinking about what that means in terms of things like graphing and all the other things we do with functions so far. Okay, so here's what we're going to try to do. We are going to do some graph transformations and think about how graphs change when we introduce different factors to them. Okay, so for this first one, this is a graph of sine x, and we want to graph on top of it what 6 sine x is going to look like. So if we were to multiply sine by 6, what does that do to our function? So this is a graphing transformation. So hopefully you remember what that means and what that looks like. You can certainly use a calculator if you have one to see the visual differences. And then we're also going to consider 3 sine x minus 2. Okay, so again, this is the sine function, just the basic function. What happens if we multiply the sine by 3 and then subtract 2 off? Okay, so I want you to think about it. I want you to think about what these graphs are going to look like once we impose these different actions upon them. And I want you to take 2 minutes to try to think about graphing on top of this graph or side by side. What this new function is going to look like. So again, these are just graphs of sine. And now we want to graph 6 sine and we want to graph 3 sine minus 2 to see what kind of differences they look like when we multiply something by sine and when we subtract something off in the second case. So take 2.5 minutes, see if you can sketch it out, think about what you think is going to happen, and then we'll go through it together. Okay, take about 30 more seconds. All right. So for the first one, we have 6 sine x. So that means that every single y value that would normally happen in just a sine x is going to go 6 times as big. So what does that mean? So that means instead of having a maximum of 1 here, right, that we see right in between 1 and 2, the maximum is actually going to be 6 times bigger than 1. So 6 times 1 is going to be 6. So we're going to sort of stick our maximum up here so we can kind of look at what's happening. Now, if sine equals 0, 0 times 6 is still 0. So we're still going to go through all the 0 spots. Okay. And then over here, we know that instead of a minimum of -1, we have to multiply that by 6. So this is going to come all the way down to -6, right? And then everything in between is also multiplied by 6. So we can kind of sketch out that this is going to have to come up here, back through the 0, down through this, back up through here towards 6 again. So what happens is we take these values and we stretch them by 6. And it's easiest to sketch out what's happening by taking commonly known values like 1 and 0 and plotting those to get a sense of where it should be. But the idea is that it's going to be stretched by 6 units as we go. So the horizontal units are not impacted when we multiply, right? So we still have a period that is the same, but now, right, we see that we have stretched the maximum and minimum values as we go. So that's what that one's going to look like. What about 3 sine x minus 2? So for 3 sine x minus 2, I'm actually going to do this in 2 steps. I'm going to do the 3 sine x first. And once we know what that looks like, we'll consider what does 3 sine x minus 2 look like. So we're going to do sort of 2 steps here. So for the 3 sine x, we're going to do pretty much what we did up here, except instead of 6, we're going to use 3, right? So we know that the zeros are going to be the same. And now the maximum, which was 1, is going to go up as high as 3. And the minimum, which was -1, will go as low as -3, right? And so we are able to sort of sketch through what this 3 is going to do to our graph. Similarly over here, right? So we get this sort of stretched sine graph. So this is y equals 3 sine x. But we need 3 sine x minus 2. So when you add or subtract a number to your function, it shifts your graph up if you add a number and down if you subtract a number, which means that we have to move this entire green graph down by 2 units. So that means instead of going as high as 3, it's going to go as high as 1. Instead of 0, right, we have to shift it down 2 units. It's going to be at -2, right? So -2. And then here we're going to move down 2 units. So we're sort of shadowing exactly what happened before, but we shift everything down by 2 units. Right? So this difference between these is 2 units. So y equals 3 sine x minus 2. So we've shifted everything down. So this shifts down 2 units. And then the 3 stretches by 3 units. Okay. So that's how we transform the sine graph into 3 sine x minus 2. Okay. We have one more to try. So we've done stretching, we've done shifting up and down. We can also shift horizontally. Okay. So here again, this is just a graph of sine x, and we want to use that as a basis to figure out what sine of x plus pi over 2 is going to look like. So I want you to think about it. If you don't remember how to shift horizontally, I will tell you it's slightly counterintuitive. But again, feel free, if you have a calculator, to graph sine x and sine of x plus pi over 2 to sort of see what's happening. You could also plug in a couple of values to see what's happening. But take a minute and a half, and see if you can sketch out what you think this new function is going to look like. Okay, take about 30 more seconds. Okay, so when we have something added or subtracted inside the argument, which is different than the last one we saw, which was outside the argument, this is going to shift horizontally. Okay, so in this direction instead of the up and down direction. And when we do it inside, to me at least, it's counterintuitive. So when we add something, we are shifting the function left. If we subtract something, we are shifting it right. Okay, so that means that we are taking the entire sine function and shifting it left by pi over 2. So that means that we're going to take sort of the peak, which happens at pi over 2, and shift it left. So we're going to move the peak to here. Okay, so that's what we're going to do. And then we're going to try to recreate this function, right, by shifting the whole thing left. So we know that at the peak, we should be coming down. So here we're going to be coming down, right? And then, right, then after we've come down, we're going to go back up. Right? And then what'll happen here is this will start to sort of turn around again, right, as we've moved it. So we've taken this whole piece and shifted it left. So the piece I just recreated was this piece here, but I moved it left by pi over 2. Okay, so we move things left and right when we add them inside the argument. Okay, so now that we've had sort of a baseline review of sine and cosine, why do we want to use it here for periodic functions? So in different types of things that we're going to model, it turns out that there are really good models for sine and cosine for a lot of things in nature, which I mentioned before. And so when we're talking about modeling with periodic functions, we are going to use what's called the general form. Okay, and the general form is y equals a sine of bt plus c, and y equals a cosine of bt plus c. So we're going to be multiplying things in front, we're going to be adding some things inside, we're going to be shifting things. So that's why we wanted to review a couple of examples of what that's going to do to the function that we're looking at. So in the general form, or I should say general forms, if you have something written like this, so there's two sort of ways we're going to use this. You'll have something written in this form, and then we get information from it, or we have information and we're trying to put it into this form, right? So it's sort of one or the other. If we have this form, right, then what we can do is we can say, okay, the amplitude of a function in this form is the absolute value of a. Right? So because sine lives between 1 and -1, and we knew that the amplitude was 1, if we were to multiply sine or cosine by some number, that is going to become the new amplitude. So when it lived between 6 and -6, right, that means that the amplitude was 6. It varied by 6 between the maximum and minimum. We have to be a little bit careful because amplitude, when we just talk about amplitude, is always reported as a positive number. So we take the absolute value to say we can go up or down by this amount. So amplitude is always going to be an absolute value. The general form can be positive or negative. So where we have to be careful, if I tell you the amplitude of this function is 7, that means if you're trying to write a general form, a could be 7 or -7. We have to look at other information to figure that out. Okay, so a up here in the general form can be positive or negative. Amplitude, we always take the absolute value and report it out as a positive number. when talking about the general form, the period is 2 pi over b. So what does that mean? So b is the number that we're multiplying inside. If there's no number in there, right, that means that the b is 1 and the period is 2 pi. That's what we know is the period of sine and cosine is 2 pi. But if there's another number in here, it scales the period in this way. So what does that mean? If you have the general form, if you know the b value, you can use that to find the period. If, however, you have like a picture or a table or something like that, and you know the period, you would need to take that number and set it equal to 2 pi over b to be able to find the value you need for the general form. Okay, and we're going to practice all of this. And then finally, the vertical shift is what it's called, is your plus c. That's how much you're going to move up or down. If c is positive, you move your function up. If c is negative, it moves your function down. Okay, so now that we have this idea that we're really interested in finding the general form, what we want to do is we want to start looking at different ways that we can have information and take that information to find these general forms. We want to find the form so we can then predict what might happen at a later point in time. And this is not trivial. These can be kind of hard. So we have to sort of put on our detective hats and figure out everything we know and figure out how to put things together. So we're going to try this. We'll do several graphs because this is how it typically comes up, but these are tricky. So the sort of steps that we're going to take are, we need to find the amplitude. So the amplitude is going to be like we did before. We're going to have it on a graph. So we're finding maximum and minimum values and using that equation we had earlier. We're going to find the period like we did before. So how long does it take for this function to repeat? And remember, if you're near 3.1, that's going to be pi. If you're near 6.2, we said that's going to be roughly 2 pi. Okay. Step 2b, we're going to use the period to find b. Okay. So if the period is 2 pi, right, then we set this equal to 2 pi. We find that b is 1, something like that. Okay. We also need to determine if sine or cosine. Okay, so we need to look at the picture and say, is this a picture that I'm looking at of sine or cosine? And again, one of the ways that I always do this is I look at, am I starting at a maximum or minimum? If I'm starting at a maximum or minimum, it's likely cosine. If it's not a maximum or minimum, it's probably sine. Okay. And then, is it rotated? Okay, so cosine by itself starts at a maximum. So if it starts at a minimum, that means it was rotated, which means it's negative cosine. Sine starts off increasing. So if you think it's a sine, but it's decreasing, it was rotated. So that's negative sine, right? So these are things we're starting to identify as clues. And then finally, we need to figure out, was it shifted, right? Did it get moved up or down? So sine and cosine are symmetric around the x-axis. So it goes up as much as it goes down. So if it's not symmetric around that x-axis, then it's been moved and we have to figure out how much it's been moved. Now, these steps can really be taken in any order. You don't have to do the amplitude first. You can do any of them, but these are the 4 things that we are trying to determine to put together our general form. Okay, so I typically start by trying to figure out, is it sine or cosine? That's just like my default, but you can certainly calculate amplitude or period first. That's all fine. Okay, so let's try this. Let's sort of see what this might look like. So here's a picture. I'm going to put this here. I'll fold this. I'm going to put these steps over here, things that we need to determine. Okay. So here's the picture we're looking at. What I want you to notice is that on the up and down axis, we're counting by twos, 2, 4, 6, 8. So then we'll have -2, -4, -6, -8. But then on the horizontal axis, we're counting by ones, 1, 2, 3, 4, 5, 6, 7, so on and so forth. So I want you to take a look at this picture. I want you to think about, is it sine? Is it cosine? What's the amplitude? What's the period? Like I said, these are a little bit hard to grapple with when you first start doing them. So just see what you can figure out. You may not get all 4 pieces, but if you get some of the pieces, that'll be really good. Okay, so I'm going to give you 2 minutes to really dive into this, see what you can figure out, see, and again, the goal is to get this into the general form, right? And so then we'll go through it together really carefully to make sure that we have all the steps. Okay, so take about 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's see what we can figure out. So again, we're looking for 4 things, but we don't need to do them in any particular order. So I'm going to start by just trying to figure out if this is sine or cosine, because that's typically what I do. And like I said, my general approach to this is I look at what's happening at 0 and I see if it's at a maximum or a minimum. What I notice here is that at 0, I'm right at the midline. So I'm not at a maximum or a minimum. So I'm thinking this has got to be sine. Okay. Now sine, we said, starts off increasing. But here I see that I start off decreasing. Okay, so this is a midline and we are decreasing. So that tells me that I'm going off of a sketch of negative sine x. Okay, so since I'm talking about sine now, remember the general form is a sine bt plus c, right? That's just like the generic general form. But now I know that I'm going to have a negative and I'm going to have a sine, right, instead of cosine. So I want to find the amplitude, so I can start off by plugging in my A. So for the amplitude here, I'm going to look at the maximum value, which looks like it's 3. Okay, so A for amplitude. So I have 3 minus, and now down here, this looks like -3 divided by 2. So again, be careful with your negatives. So 6 divided by 2 equals 3. So my amplitude is going to be 3. So what that tells me so far is that I have y equals -3 sine something something, possibly plus something. Okay, so that's sort of my sketch. The negative comes from the fact that this is a rotated sine. It was decreasing. And so I just pulled the negative to the front. That's totally normal. So again, the amplitude is reported as positive, but in the model, it can be positive or negative depending on what the graph is doing. So let's look at the period next. Okay, so the period, we're going to look here. I start at 0. And I start repeating a little bit after 6. And we said, okay, for a little bit after 6, that's 2 pi. So here, my period is 2 pi. So then I go to my equation for the period. So 2 pi equals 2 pi over b. So I can multiply the b up and bring the 2 pi down. And I get that b equals 1. Okay, so once I know the b value, I come up here. Usually we don't write a 1, right? If it's just 1, we just leave it as whatever the variable is. Here, you can write the 1. You don't have to write the 1. And then I don't know if you can see this. So if you didn't notice, this is totally fine. But this axis is labeled x, which means that my variable that I need to use is x. So again, be careful with the variable. Sometimes it's x, sometimes it's t. You have to use the one that's given. And then I need to figure out, was it shifted? There's sort of 2 ways to figure this out. The first is, does it go between the same maximum and minimum? So if it goes to 3, does it go to -3? Yes, so it's symmetric. So it actually has not been shifted. So here, I would have a +0. But another way that you can do the shift that I'll mention here, you have to be a little bit careful not to confuse it with the amplitude. But you can do the shift by doing the y maximum plus the y minimum divided by 2. So the amplitude is minus and the shift is plus. So for us here, we could do 3 plus -3 divided by 2. 3 plus -3 is 0. 0 divided by 2 is 0. So there's no shift. Okay, so what is our final equation here and what would it look like? So here we would write y equals -3 sine x, right? Because our plus c, that's a 0, and we don't usually write the 1 inside. So now we've determined what the general form is from this graph. Like I said, these take a little getting used to. So if you didn't get all the pieces, that's okay, but hopefully you got some of them, right? Like if you got that the amplitude was 3 and you figured out it might be sine, that's a good start. Or if you figure out that it wasn't shifted, right? The more we practice these, the better we get. So let's try another one. We're going to do the same thing. So here's our picture. Again, we're counting by 2s on the y-axis and 1s on the x-axis. So we're trying to figure out a general form for our function. So again, you don't have to do anything in any particular order, but we need to figure out the amplitude, the period, the shift, and if it's sine or cosine. So take 2 more minutes, see what you can figure out, see if you can determine what the function is going to be here, and then we will go through it together. Okay, take about 30 more seconds. All right. So again, we don't have to do this in any particular order, but we do need all 4 parts. So I'm going to start by just taking a look at this to try to determine if it's sine or cosine. So I'm going to go to the 0, 0 point to see what's going on there. And what I noticed is that this is at a maximum, right? It's right at the top of the hill, and that I start off, decreasing. So if I start off at a maximum, what that tells me is that this is likely going to be a cosine function. Okay, if I started at a minimum, it would be negative cosine. But since it's at a maximum, it's going to be positive cosine. Okay, so now let's consider what the amplitude is going to be here. Okay, so the amplitude, I'm looking for what is the maximum and minimum. So the maximum looks like it's at 3. The minimum looks like it's at 1 divided by 2. So 3 minus 1 is 2. 2 divided by 2 gives me an amplitude of 1. So I have 1 cosine so far. And again, we don't usually write ones. So now let's talk about the period, right? So for the period here, I started here and I see that it repeats just about here, which is a little bit after 6. So again, if the period is a little bit after 6, it's likely 2 pi. That's the same period we had before. So we take the period from the graph. We set it equal to the formula, which is 2 pi over b. And that tells me that b has to be 1. That means so far, I have y equals 1, which I'm not, well, I guess I will write 1 cosine x. But I can see visually that cosine, that this is not just a cosine, right? Because cosine lives between 1 and negative 1, and that this has been moved. So I need to figure out the shift. Okay, and as I said before, we can take the maximum value plus the minimum value divided by 2. So I have 4 divided by 2, which equals 2. So since it's positive, I have plus 2. So I have a cosine function that's been shifted up by 2 units. That's what I see here visually from this graph. So this is my final formula. Okay. So let's try one more, right? So hopefully you're getting used to taking in the different types of information, how we're calculating it, how we're putting it together. Okay, same idea. I'm going to give you a minute and a half on this one because I want to make sure we get to the last problem. But see what you can figure out. See which pieces feel okay. So give it a try. We'll go through it in about a minute and a half. Okay, take about 30 more seconds. All right. So let's start with the amplitude and the vertical shift, since those are both related to the maximum and minimum values. So I notice here that the maximum value is 4. And then the minimum value is -4, right? So with amplitude, I do 4 minus -4 divided by 2. And with the vertical shift, I do 4 plus -4 divided by 2. So these both rely on the maximums and minimums. So for the amplitude, I have 8/2, which is 4. For the vertical shift, I end up with 0/2, which is 0. So by determining the maximum and minimum values, we get 2 of the 4 pieces of information that we need. Okay, so now let's talk about whether we think this is sine or cosine. So again, I'm going to go to x equals 0, and I notice I'm at a minimum. Okay, so if you're at a maximum or a minimum, you should be thinking cosine. Since I'm at a minimum, that's going to lead me to negative cosine. Okay, so I should have something in terms of negative cosine. So putting together what I know so far, I have y equals, I'm going to pull the negative to the front. My amplitude is 4, so -4 cosine. I haven't done the period yet, so I'll leave that blank. And then I don't have a vertical shift, so I don't need to add anything on at the end. So the question that remains is about the period. So let's look at what's happening here with the period. So if I look at this function and when it starts to repeat, I notice that this one seems a little bit different than the others. It's a little more condensed. And so when I look at where it starts to repeat, it's a little bit after 3. And so my speculation here is that the period is pi, right? Because it repeats again a little bit after 6, so another pi, 2 pi. So the period here is pi. So what I need to do is I need to take pi and set it equal to the period formula, which is 2 pi over b. Okay, I'm trying to solve for b, so I bring the b up and the pi down, and I get b equals 2. So that means back in my formula, I have a 2, and then my variable again is x. So I have -4 cosine of 2x. Okay. So hopefully these are starting to make sense. The more you do of them, the easier they get. Okay, so I want to make sure we get to the last problem here. This is a word problem where we are doing the same type of thing. We're trying to determine the formula, but based on a word problem. So typically with word problems, you're not going to have the graph, but I do find it helpful to graph it. So we'll just do this one together and we'll talk it through. So this says Boston averages 15 hours of daylight in June, 9.5 in December, and 12 in both March and September. Assuming that the number of hours of daylight varies periodically over a period of 1 year, write an expression for n, the number of hours of daylight, as a function of t. Let t be in months and t equals 0 corresponds to the month of June. Okay, so there's a lot of information here. So let's start with the fact that t equals 0 corresponds to the month of June. So that means we're starting our function in June. And what do we know about June? Well, in June, Boston's getting 15 hours of daylight. Okay, so if we were going to graph this at time equals 0, the number of hours of daylight would be 15. Okay, so we can just mark that. This is time equals 0. This is June. Okay, we know it's periodic, but let's see what else we sort of know about the whole thing. So in December, we have 9.5 hours. So if we're in June, we can just count July, August, September, October, November, December. So that's 6 months later. We know that the number of hours of daylight is 9.5. Okay, so we have a point there. And the reason I'm graphing this is to get a sense of if this is sine or cosine, just so you know why I'm choosing to draw a picture. So we also know that in both March and September, we're expecting 12 hours of daylight. So June, July, August, September. September is 12. So here we go up to 12. And then also March, so December, January, February, March is also 12. And then we also know that when we get back to June, we should be back up to 15. So this was March, April, May, June. So after 12 months, we're back up here. Okay, so we have a function that is decreasing and then increasing, right? So since this is periodic, we expect it to look like this, right? But nothing crazy is happening in between. It's either going to be sine or cosine. Since we're starting at a maximum, right, that tells me that I should really be thinking about this in terms of cosine. Now here the variable is t. Okay, now what else do I need? I need the amplitude. So the amplitude is the maximum value, which is 15, minus the minimum value, which was 9.5, divided by 2. That's going to give me 2.75. Since I started at a maximum, that was positive cosine. So far I have 2.75 times cosine of something, right? So I have my amplitude, I know it's cosine. Let's talk about the period. The period is 12 months, right? It takes 12 months to repeat. Every 12 months, it starts again. So for the period, it's 12. So we take 12 and set it equal to 2 pi over b. Now we're going to solve for b. So b equals 2 pi over 12, which is the same as pi over 6. We can put that into our formula. So we have pi over 6t. And then the last step that we need to do is figure out the shift. So for our shift, we're going to take the maximum plus the minimum, divide by 2, and that's going to give me 12.25. So that's the last thing we have to add on here, plus 12.25. So our final equation that models this scenario looks like this. Now the amplitude, the period, and the shift, we could get without a picture. We can just use the numbers because we have maximums and minimums here, and we can figure out that the period June to June is 12. But to figure out if it's sine or cosine, you really need to figure out, are we starting at a maximum or a minimum? Are we increasing, decreasing? Okay, so try out that homework. On Thursday, we'll be starting chapter 2. So I will see you then.